Welcome back to Honors Calculus. In this video, we're going to be looking at infinity. We've talked about infinity a little bit before, so to be more specific, in this video, we're going to be looking at how we can use limits to define behavior around infinity. Let me get my head out of the way and let's jump right in. We're going to define the limit as x approaches c of f of x is equal to infinity, if and only if. Instead of an epsilon, we're going to use a capital M here. For all capital M greater than 0, there exists a delta greater than 0 such that f of x is greater than m whenever x minus c is less than delta. And to make sense of this epsilon delta definition, which doesn't have an epsilon in it, but still holds to be the same sort of thing, let's take a look at the graph y equals 1 over x that we've used a couple of times. What we're saying here is that if I pick any value m, I can find a delta so that in the interval in question, my function is always bigger than m. Right? This is a nice way of defining a vertical asymptote. Unfortunately, it's not the only way of defining a vertical asymptote, because an astute viewer will notice that, well, if we're over here, we're definitely not above m, we're actually way down there instead. And so the limit of as x approaches c of f of x is equal to the negative of infinity if and only if for every little m less than 0, there exists a delta greater than 0 such that f of x is less than little m whenever 0 is less than the absolute value of x minus c is less than delta. And for the graph of the 1 over x function, we even break that up further. So the limit as x approaches 0 from the right of 1 over x is equal to infinity. And the limit as x approaches 0 from the left of 1 over x is equal to negative infinity. The goal on all of this is to try to fit a formal definition into what infinity means and try to find a way to say something is equal to infinity. Before I get any further, I want to stress, infinity is not a real number. 1 over 0 is not equal to infinity. That is a meaningless thing to say. But the limit as x approaches 0 from the right of 1 over x is equal to infinity. It's a subtle distinction, but it is a distinction and it's an important one. Infinity is not a real number. For 1 over x to be defined, it has to be a real number, right? Real numbers are closed under division, except for dividing by 0. And so we have to be careful of our language. The limit is zero, the function, I'm sorry, the limit is infinity, the function is not infinity. I also want to take a moment here and mention that we really don't have an analytical tool for finding out whether a vertical asymptote has a limit of positive infinity or negative infinity. In order to do this, we're going to look at the graph. We're going to determine if the graph goes upward or downward on the left or on the right, and then we can use the definition. We call it an epsilon delta definition, even though there's no epsilon, but we'll use that definition as a way of setting and proving that the limit is infinity or negative infinity. For the sake of time in this course, I'm not going to take the time to do that, but that is how we would approach it if we needed to. And so that's our idea moving onward. Instead, I want to take this idea and flip it around, because the function going to infinity or negative infinity is hard to deal with, but x going to infinity or negative infinity is something we can deal with. So let me get my head back out of the way. And we want to look next at the idea of end behavior. The limit as x approaches infinity of f of x is equal to L if and only if, for all epsilon greater than 0, there exists a capital M greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever x is bigger than M. Right? It's the definition of limit equals infinity kind of flipped backwards. We switched where our bigger than M is going, but it's the same idea. And once again, to make sense of it, I want you to think about this in terms of the graph. So if we have some, let's call it an oscillating function that is oscillating smaller and smaller, what we're claiming is that we can find some cutoff point so that the function stays bounded above and below everywhere to the right of that cutoff point. To the left, it may not, but to the right, it does. And just like we had with limits of infinity, we can also look at the limit as x approaches negative infinity of f of x is equal to L, if and only if, for all epsilon greater than 0, there exists a little m less than 0, such that the absolute value of f of x minus L is less than epsilon whenever x is less than little m. All right. So I've got one theorem about limits at infinity, about end behavior that I care about right now, and that's that the limit as x approaches infinity of 1 over x is equal to 0. And this is just taking the definition, the limit as x approaches 0 from the right of 1 over x is equal to infinity, and flipping it on its head. It's the exact same notation even. And I love that proof because it's an epsilon delta proof where I don't have to write an epsilon or delta. Right? Because of the fact that the limit as x approaches 0 of 1 over x is equal to infinity, that must mean taking the reciprocal of both sides, that the limit as x approaches infinity of 1 over x is equal to 0. And likewise, the limit as x approaches negative infinity of 1 over x is equal to 0, because the limit as x approaches 0 from the left of 1 over x is equal to negative infinity. I'm also going to assume, without even stating it or writing it down, that the limit as x approaches infinity behaves the same way as all the other limits, so we can go through and we can use all the same properties we've been using before. So for example, if I want to take the limit as x approaches infinity of x squared plus 3x plus 4 over x squared minus 2x plus 5. Well, if I try just plugging in infinity, I get infinity squared, which is infinity, plus 3 times infinity, which is infinity, plus 4, and infinity plus 4 is still infinity. Then I get infinity squared, which is infinity, minus 2 times infinity, and infinity minus infinity is actually still infinity. It's easier to deal with that way, and then plus 5 is still infinity. And infinity divided by infinity is another indeterminate form. And we're going to use the same tool we used for the original indeterminate forms. Let's see if we can find a way to rewrite this fraction so that it doesn't give us an indeterminate form and is equal everywhere except for the problem point. And what I'm going to do is I'm going to take the biggest power of x that appears in the fraction. In this case, it's x squared. And I'm going to divide numerator and denominator of the fraction by that thing. As long as we're not near x equals 0, this isn't a problem, right? X equals 0 would be a problem, but when we're looking at x equals infinity, we're looking at values of x that are much bigger than 0, so nothing to worry about. And that gives us a really ugly looking fraction. But we can evaluate this thing. And this should go to 1 plus 3 over infinity plus 4 over infinity squared divided by 1 minus 2 over infinity plus 5 over infinity squared. And now's probably a good time to mention that my academic background is in physics more than it is in mathematics, although I do have a graduate degree in mathematics. And that's important because I just did this limit the way a physicist would do. A mathematician would look at this and say, no, that's evil. You can't write that. 3 over infinity, that doesn't make any sense. A physicist says, well, writing 3 times the limit as x approaches infinity of 1 over x is just too much writing. So we just define that as 3 over infinity. It's a shorthand. It means the same thing. It's a shorthand. But something divided by infinity is equal to 0. That was the theorem we proved. And the limit of something squared is the square of that limit. So this is also going to be 0. And that's going to be 0. And that's going to be 0. And we are left with 1 over 1, which is 1. There are a bunch of other things we can do with end behavior, and we'll be coming back to this topic a little bit later on in the course. But I wanted to bring it up at least a little bit right now and talk about how infinity works and how infinity works around limits. So to wrap up, I have this one for you to try. The limit as x approaches infinity of 3x squared plus 2x plus 5 all over x cubed minus 1. See what you can come up with this one, and I'll see you in the next video.